want to thank the organizers, St. Christophe, for giving me a chance to present these results in this wonderful conference. Okay, so let me start with a rather long introduction, and I'm going to talk about the total population size, which is, of course, a very important characteristics of many ecological systems on its own, but the total population size is also often required as input information in many ecological problems. So we can ask for this information in the problem of monitoring. We can ask for this information when we have to make some control decisions. For instance, when we deal with insect pests, whether or not to apply pesticides based on the total population size of the pest population. We need this information in the problem of synchronization, the problem I'm going to discuss a little bit later on in my talk, and we may think about many other applications. So how can we obtain the total population size? The most straightforward way is to obtain it by direct counting, like in this peaceful picture. So some people count sheep to get asleep. Ecologists and farmers count them to obtain the total population size, and obviously the answer is exact. So we do know that there are, for instance, 275 sheep in this particular field. However, if we think, for example, about aphids, so aphids on a single leaf can be counted if we have some time and patience. When we go to a field, we immediately realize that it's now impossible to count all of them because the distribution is not uniform. So we cannot do it just by mere multiplication. So the number of aphids, the number of leaves, the number of plants in a row, the number of rows, because the distribution is not uniform, and therefore we have to come up with some method of evaluation instead of direct counting. And once we have agreed that we must evaluate the total population size, an immediate conclusion is, because we use this information about the total population size as input information in the many ecological problems, therefore, if we are not able to come up with accurate evaluation, then we may end up with very wrong conclusions about our ecological problem, where this total population size is used as the input information. Therefore, my talk is about how accurate or inaccurate our evaluation of the total population size can be. So we first talk about sampling procedure for spatial population distributions. We will discuss accuracy of this sampling procedure, especially accuracy of what we call coarse grids. And we will see that actually we have to revise standard methods of evaluation. We have to deal with a probabilistic problem rather than deterministic. And we will discuss how to deal with a singularization of a random variable, which is essentially what we have on coarse grids. And then I will give an example of consequences of what may happen if our evaluation is inaccurate, so how it may affect our conclusions about synchronization of population fluctuations. Okay, so sampling procedure for a spatial distribution. We make several assumptions. So the first thing is we consider fixed time t. Okay, so we deal with the spatial distribution. This the population is confined within a certain domain, and we assume that within that domain our population can be monitored and sampled, and we use what I loosely call detectors, because there is there are a variety of sampling device. So we may think about the traps, soil cores, nets. I will show you some examples a little bit later on. So those detectors are installed over the domain. And another very important assumption is that we assume this sampling procedure brings us reliable information, so accurate information about the population density. How can we get that accurate, exact information? That is a different problem. I'm not discussing it here, but let's just make this assumption. And we have exact values of the population density function, but we have them just at sampling locations. And given that information, we must evaluate the total population size. So first, as I promised, there are some examples of what we may call detectors. So a very simple picture, I made it myself somewhere in Shropshire. So slag trap in the wheat field looks like a plate. Actually, there is a plate, so it's a very simple trap. This picture, something that looks like a stick, but in reality it's something much more sophisticated. This is an acoustic device used for bat detection. And I'm going to talk mainly, so mention just traps, but I just want to demonstrate that we may deal with something much more sophisticated rather than this particular plate, or like in my next picture, we may use a plastic cup and still it will be considered like a trap. Okay, so this picture, however, is about the geometry, because it's not very often we deal with a single trap. Normally we have a grid, okay, and two basic cases are that we may have a one-dimensional grid, okay, and if you look carefully you will see a two-dimensional grid of traps here, and in both cases grids are regular, so the distance between neighboring locations, between neighboring sampling locations is always the same. That is another important assumption, actually. So, if we use the density function everywhere, that would be a very nice mathematical problem. So, by the definition, the total population size is given by the integral, because this information is given to us at the sampling locations only. So, more mathematically speaking, at grid points of our grid. We have to replace our continuous problem with a discrete problem, and we therefore, instead of computing the exact integral, we make this evaluation. So what ecologists do, they compute the average and multiply with the area of the domain. And because we replace the exact answer with some approximation, with some evaluation, we have to introduce the evaluation error. So this is just the definition, and that is how accurate we want to be. So in our ecological problem, normally we have some specified tolerance, and we want our evaluation error to be within those limits. Okay, so looks like very simple and straightforward. What is the problem then? The problem is that in very many cases, we are not able to install as many traps or more generally as many sampling devices as we like. So for many serious reasons, our resources are limited, and we therefore have to deal with what we call a coarse sampling grid. And loosely speaking, this definition means that either we don't have a sufficiently large number of samples, or from a geometric viewpoint, the distance between neighboring sampling locations is too large. What do we mean by these words? too large or not large enough? This is actually a very big and challenging question, and I'm going to discuss it a bit later on. But what we can immediately conclude is, okay, if we don't have a sufficient number of samples, that means we don't have sufficient information about the population density function. That may result in an accurate evaluation of the total population size. And once again, if we use the total population size as input information in our ecological problem, then that may result in incorrect conclusion about the ecological problem. So let us see what we have when we try to evaluate the total population size on coarse sampling grids. And I want to consider two extreme cases. And because they are extreme, they were not taken from real-life data. Both these examples have been generated from a mathematical model. And the beauty of mathematical model is, of course, that you may take any number of grid points and deal with your solution function. So the first picture and the first density distribution, so over here we have a really fine grid of points, 64 by 64, and that is how our density distribution looks when we use this grid. The grid is fine, but it's not realistic, okay? Now, let us consider a realistic grid, 9 by 9, and take the values of our density function and try to reconstruct our density function given just the information at grid points over this relatively coarse grid. So what we can see, so there is a very similar picture, so we still can see all features of our density function. And even if we consider a very coarse grid, 3 by 3, okay, so maybe not so good resolution, but still something that looks, okay, more or less reasonably well. So this is what I call distribution 1. Now another extreme case, it's a highly aggregated density distribution. So we have a local subdomain of the non-zero density, okay, which appears as a collection of smaller patches. What we see if we now try to reconstruct this density function over this grid, actually we see nothing, because we can see a small spot, but this is just because of visualization. If you look at the legend, then you realize all values are very close to 0. The same is on this grid, where again we have something that is, in reality, it's just 0. Okay, so what then happens when we try to evaluate the total population size for the first and the second distribution? How the information about the density function available to us will be translated into the answers that we have on a realistic grid. Okay, so there is a grid 5 by 5 nodes shown here, and we can see that in the first case we have really very, very accurate evaluation, because the error is of the order 10 to the minus 2, and in many ecological problems, so we require something like, say, okay, so normally it's of the order of 10 to the minus 1, so it's much, much better than required accuracy. What we have here, well, basically we have nothing, because if we look at this picture carefully, we will see that this grid, when we install it, we miss the whole subdomain of the non-zero density. So we have 0 at any grid point, and therefore, as a result of our evaluation, we have something strange, and that is reflected in the error of 100%. Okay, let us document these very simple and expected results. And we have this diagram. Okay, so we have the true answer, the exact answer for the first distribution. We have the exact answer for the second distribution. And our evaluation is accurate, it's close to the true answer in the first case, and it's not so accurate in the second case. What we can see, some quite obvious things. We may either have low accuracy of evaluation, or we may have high accuracy of evaluation, and the whole thing seems to be quite deterministic. So we go to the field, we install our grid, we collect data, we obtain our evaluation, then either we are happy with that evaluation or we are not happy, but that seems to be predetermined. However, there is one observation which is crucial for our discussion, because when we have a fixed grid of endpoints, our accuracy depends on a special pattern of the density distribution, okay, so we could see it, but also it depends on the location of each grid point. So what do we mean by this statement? We don't know when we go to a field and we install our grid of traps or whatever we use, we don't know actually, in this case, either the exact location of this non-zero density subdomain. In this case, we don't know what is the exact location of the front that separates zero and non-zero domains. Therefore, what happens if we move this entire spot of the non-zero density just slightly, if we move it to the right, or in other words, which is equivalent, if we move the whole grid slightly to the left. So in this case, I just demonstrate one grid line and one grid point, okay, but if we make this experiment, then we realize, okay, so we move this node, this node, this node, all of them to the left, the values we will have, they will be just slightly different, okay? Therefore, the error I can expect here is of the same order, okay? So still I have very good evaluation, very accurate evaluation. What happens in this case? If I move all grid points to the left, or in other words, once again, I move my density distribution slightly to the right, again, I will have zero values of my density function at any grid point, apart from this single point where occasionally I may have a really very high value of the density distribution. And when I then average it, because we remember the formula, so we have the average and we multiply with the area of the domain. So when I average it, again, occasionally, but I may get even more accurate evaluation of my total population size than I have in this case. Therefore, if I want to revise my diagram, I have to provide something very similar for the first distribution. My error is the same, okay, of the same order. Not the same value, of course, but of the same order. But in the second case, I have something that is really different. And because my answer depends on the location of each grid point, and that is true, once again, because we don't know in advance the features of our density distribution, okay? Therefore, we don't know what is the optimal location of each grid node. Because of this, I figure out that my evaluation result can be considered as a single realization of some random variable. So I install my grid in this way, I get something, I install it a slightly different way because I don't know, okay, what is the most optimal way, and I have something very, very different. What I want to say here, because sometimes people get confused, this uncertainty appears because we don't have sufficient information about the density function. Okay, so that is because actually we have this coarse grid, okay, and we don't know where this spot of non-zero density is located. it has nothing to do with the measurement errors. So because our assumption is that we do have exact, accurate values of the density function, but we don't have sufficient number of them. So we don't have sufficient information about the density function. Okay, so let us now try and document the results of our evaluation once we have agreed that actually this evaluation must be considered like a random variable. I want to skip some mathematics and just say some magic words like it can be shown. So it can be shown when we have this nice, smooth density distribution. All realizations of our random variable will be close to the true population size. So my diagram will look like this. So that is my range. The range is not so big, so the variance is small. And therefore, any single realization of our random variable can be considered as a good approximation of the true population size. And another statement, which does not sound quite mathematically, but we can provide a more strict mathematical formulation is, okay, so we have all realizations of this random variable with almost equal probability. So crudely speaking, that means we go to the field, and in this case, wherever we install our grid, we still we will be accurate. So we will have accurate evaluation. What about this case? The results are very different. First of all, the range is big, and we could see it. The mean is not close to the true value, the variance is big. Therefore, again, we could see it, only some realizations of this random variable can be considered as good approximation of the true population size. And another important observation is that, of course, the probability density function of our random variable is not constant. And again, crudely speaking, that means it's more likely that we will see inaccurate realizations of our evaluation. So again, we go to a field, we install our grid. In most cases, we will just miss this distribution. Okay? In some cases, yes, we will be lucky to catch it and to get accurate evaluation. Okay, so this motto is what the British Queen would say if she had to deal with the problem of total population size evaluation. So the motto of the royal family is keep calm and go on. In our case, it's translated like keep calm and refine the grid. So things are not, in theory, things are not so desperate because we do know from the theory that if we increase the number of grid points, sooner or later we shall converge to the exact answer. But that sooner or later is actually a very big question for us, given that in reality we have to deal with grid that have rather relatively small number of points, and how fast we can obtain accurate evaluation, that is a big question. But let us keep it in mind, okay, so that in some sense that is the discouraging the encouraging result, that we are able to obtain an accurate answer if we deal with a relatively fine grid. Okay, so once we have agreed that we have to deal with a random variable and we have to deal with a single realization of that random variable, what can be done? Because it's quite hard. So when people think about some random variable, so they may ask questions, okay, what is the mean, what is the variance? It's quite hard to say anything having just a single realization. So the first step is to move from the evaluation to the evaluation error because it's more convenient for many reasons. Immediately we understand that our evaluation error is a random variable as well because of this, okay? And it depends on the number of grid points, okay? So on fine grids, it's going to be very small. On coarse grids, it can be very big. It depends when we fix the number of grid points. It depends, as we could see, on a special pattern of the density distribution, location of each grid point, okay? We have discussed it. And then let us ask ourselves, so we have to deal with this random variable, but do we really need the mean and the variance, all that information? And actually the answer is no, because what we want to see is that our error is less or equal that specified tolerance. So we want to see that our evaluation is accurate. And if we cannot provide accurate evaluation, then we should be able to answer the question, what is the probability of this event? So again, we go to the field, we install traps, we have something, what is the probability that we are accurate? Okay? And then the next question is, okay, now if we are allowed to add some points, okay, to increase the number of points of our grid, again, sooner or later, we will be accurate. And that question can be reformulated like, what is that threshold number of grid points to provide the probability of this event, so our error is less than specified tolerance, and the probability is equal to 1. And at this point, actually, we can reconcile our probabilistic and deterministic approach, because if this condition holds, we still have certain range of our random variable, but we don't care, because for any single realization of this variable, if this condition holds, we don't care about the value of that realization. We just know that we are accurate, and we therefore can consider the whole problem as deterministic in that sense. So these are big and challenging questions. We don't have a general theory how to handle them. So today I just want to show some examples and some, let's say, smaller questions related to this problem. And simple one-dimensional examples, if we have, for instance, this quadratic function, which is a single peak, so from ecological viewpoint, that is highly aggregated density distribution again. And we don't know, so this is our domain, and we don't know actually where this peak is located within this domain. What is the number of grid points required to install that we can guarantee this condition wherever the peak is located? And in this simple example, we were able to derive a theoretical result. So this is a theoretical curve. The probability as a function of the distance between neighboring grid points. So how do we read this graph? Okay, so when we have a coarse grid, the distance is really big. Okay, so we may have just probably 2 or 3 grid points. The distance is big. The probability that we will be able to obtain accurate evaluation is small. Okay, so this is the value of h. We are somewhere here. So if we have a very fine grid of points, we are able to capture our peak wherever it's located. Therefore, h is small. The distance between neighboring points is small. The probability is 1. We always guarantee accurate evaluation. So this is therefore the critical grid step size, okay, and we can figure out the number of grid points. The theory says in this case that this value of the critical distance depends, so it's related to the peak width, okay, which is probably quite expected result, and it's further illustrated. So now we have different different distribution, so still a peak, okay, but given by different mathematical expressions, that's the Lorentz distribution. What if we have a wider peak, okay? So the probability on a fixed grid is always higher than if we have a very narrow peak. So our chance to get the accurate answer is much higher. Obviously, the results also depend on the accuracy we require. So again, we have some distribution. We require the same condition. Now we want to have really very accurate evaluation and maybe not so accurate evaluation. Obviously, then when we have fixed grid of points, the probability will be higher if our accuracy requirements are not so demanding. Okay, so conclusions for this part. So I guess I still have some time. Yeah, okay. We have to understand that when we deal with coarse grids, then we have to handle our results from a probabilistic viewpoint. And in some cases, we could see it, we can think about of a single realization of our random variable as of a deterministic variable, okay? But in many cases, we just cannot. And in this case, we have to try and compute the probability of accurate evaluation. So this is especially true for highly aggregated density distributions. And therefore, our definition of grid causelessness does not depend on number of grid points. It depends on a spatial pattern of the density function, which is actually another important conclusion. So we cannot say, oh, 3 points is always a coarse grid, 300 points is always a very fine grid, because we may have situations where 3 points will give you a fine grid, you will already have accurate evaluation, guaranteed, and you may have situation, very narrow peak, for instance, 300 points will not be enough to end up with accurate population size. Okay, so now let us go back and remember at the beginning we agreed that yes, so the total population size is input information in many ecological problems. So what happens if we have inaccurate evaluation of the total population size? And I want to illustrate with this problem with the example of synchronization. So what is synchronization? Okay, maybe a bit loose definition, but people talk about synchronization if they see some population fluctuations in different habitats. So now we introduce time into our problem, and those population fluctuations, they can be, they appear to be correlated. And this is one example taken from the paper by Grenfell with coarses. And what they did, they monitored the total population size, so year by year. And it was done on 2 islands close to the Scottish coast. And we remember, so the total population size in case of sheep, okay, can be obtained exactly. So we just count them head by head, okay. And we will see that the population size is different, but fluctuations seem to be pretty similar, okay. And in this case, we talk about synchronization between those populations. A lot of studies, so the problem of synchronization is an important problem. A lot of studies, I just want to mention 2 examples, probably not the most well known, but quite illuminating. So the first says that actually this synchronization can be revealed not just between 2 habitats, but like in this case, 8 or even more in some cases. People also talk about cross-species synchronization. So in this case, caribou and musk ox. And this example actually also gives us some amazing distance, so 1,000 kilometers of inland ice in Greenland, and still they could see a correlation between population fluctuations. So, of course, a lot of information in the literature, so some references, and also the discussion of mechanism of synchronization. It's another very big and challenging problem. I'm not going to talk. I think Ellen is here. Ellen knows much better. If you want, you may ask him. Okay, but my talk is not about mechanisms of synchronization, but about the consequences of inaccurate evaluation. Because, so the total population size is input information. How do we reveal synchronization? If we have field A and field B, we have to introduce some scalar characteristics, and in most cases, this scalar characteristics is the total population size, and we evaluate this total population size at certain times. Okay, so we have 2 time series, and then we just calculate the Pearson correlation coefficient between those time series. So this is the definition, just to show you that yes, so for the correlation coefficient, we have our total population size as input information, okay? So this is another example. And so we can see from the picture that, okay, fluctuations seem to be correlated. Now this result is scientifically confirmed. The correlation coefficient is really very high. And then let us ask ourselves, what happens if these values are not very accurate? And actually, this is not a very straightforward answer, because synchronization is not about accuracy, it's about tendency, okay? So we may have, if you look at this picture, we realize we may have the population size like 10 or maybe 25, but then if it goes down, we actually don't care how big or small it is. What we want, it's just the trend, okay? It's going down or it's going up. And we may ask, why should then we bother about accurate evaluation? If we are able to capture some trend, then our conclusions about synchronization will be quite correct. And if we have revealed synchronization in some ecological systems, then of course we may enjoy many implications, because obviously, if for instance we have my favorite problem, the problem of insect pest control, we have 2 fields, and if we are aware about synchronization between those 2 fields, then we can save our resource and have just monitoring of the first field, and any conclusion we may then have about the first field will be true and correct when we apply for the second field as well. But again, in order to do such things, we must be aware that we do have accurate information, we do have accurate conclusions. Let us see therefore, what happens when we use coarse grids for our evaluation. And let us have a look at what we call true and false synchronization. Okay, so what we did, we have constructed several examples, very simple one-dimensional examples. And in the first example, we had our special temporal distribution. So once again, we have introduced time. So our density function now depends on time. And we say, okay, let us have something in field A and field B. And the temporal component of our distribution will be the same in both cases, okay? Therefore, our population dynamics is perfectly synchronized. We must expect the correlation coefficient equal to 1, no matter what spatial component we have here. And what we did, we considered the spatial distribution as a superposition of several normal distributions. So in other words, superposition of several peaks, okay? And the location of each peak is a random variable. So we generate the superposition of several peaks in the first field, in the second field, okay, but they have the same and very simple temporal component, so just given by a linear function. So this is one example. This is a superposition of 4 peaks. So we don't know, once again, the exact location of each peak. Okay, and let us see what happens when we evaluate the total population size under these conditions. Whether or not we will be able to reveal synchronization. So let me explain this graph. What we do, we say, okay, n is the number of grid points. Let us start with the coarse grid. So if you go back to the spatial domain, we install probably 2 or 3 grid points for our sampling. Okay, we have a single peak here, which, as we probably remember, is actually a tough test case, because if the peak is narrow, then our chance to capture it is not very high. And then we have, for this single peak, we have this peak can be wide. Okay, so go back to this definition. Okay, so, and or it may be narrow. So if we start with a wide peak, okay, then we know, again from our previous discussion, sooner or later we must capture the peak. So when we have a sufficient number of grid points, we therefore, when the number of grid points is big enough, okay, then we must converge to the true value. So we must have the correlation coefficient as 1. But if we have a coarse grid, if we have just 3 or 4 grid points, then we obtain something that is really far away from the true value of the correlation coefficient. And this situation is even worse, and again, it was predicted. We understand when the peak is narrow, okay, then again, sooner or later, we must converge to the true value. But the number of grid points required to resolve this peak is obviously much bigger, so convergence is much slower. Okay, so the same was repeated, but now it's superposition, 1 peak, 4 peaks, or 8 peaks, and we can see that in the case of 8 peaks, our results are much better. Okay, and again, so naive explanation is that yes, so our density function, because it's now superposition of 8 peaks, it fills somehow the whole domain, so we are able to get something, some information about it, even on coarse grids. When we have 1 peak, then again, so on coarse grids, we may just totally miss it. Then we changed the temporal component of our density distribution, so considered something more sophisticated, the Rieke map, and we could see that actually the problem is just with the spatial component, because the results were the same. Again, we have a coarse grid, we don't resolve our spatial distribution, and we have something wrong. Okay, so then we increase the number of grid points, and we have a correct answer. And finally, let me mention another example of what we call false synchronization, or sometimes we call it ghost synchronization. That is how the title of my talk appeared. And this situation is when on coarse grids, because of inaccurate evaluation, we may observe the correlation coefficient, which is pretty high, and we conclude about the existence of synchronization. But in reality, the dynamics is not correlated. So what we did here, again, we considered 2 spatial temporal distributions in field A and field B. And now we select these functions, omega and sigma, in a way that our density distributions are not correlated. So if we consider for the first field, we consider these definitions, and for the second field we have these functions, and we can see that actually in the first field the population will grow with time, in the second field and it will decrease. Okay, and the spatial distribution is given by this function again, so the exponent. And what we do next? Let us think about a single sampling location where we have the value of the density function that grows with time in both cases, okay, because of our definition of those functions. This is just one point, but if we use this point as a sampling location, okay, then obviously our correlation coefficient will be positive. So in reality, it must be negative, okay, and it's -1. And but if we use just this point for sampling, then we must get a wrong answer, okay, and this is confirmed. So if we use just one sampling location, then we have something that appears to be strongly correlated. But amazingly, if we now add more points to the grid, we have something that appears to be even stronger correlated. So again, I want to emphasize, if we keep adding points to our grid, to our sampling grid, then sooner or later we must converge to the true value. So we must obtain the correlation coefficient, which is -1. But on coarse grids, we have something that is very far away from the correct answer, and we call this phenomenon as false synchronization. So in conclusion, so basically, when we have a sampling procedure and we have a coarse grid of samples, we must be very, very careful about the results of our evaluation, because we could see inaccurate evaluation, again, is bad, is dangerous on its own, but if we use this information as input for a different ecological problem, then this ecological problem, in my case, that is a problem of synchronization, and the results of the conclusions about that problem will be affected as well. Okay, so in particular, we must be careful when we deal with patchy population distributions, because we could see, so we may have really very inaccurate evaluation on coarse grids. And perhaps this is the most important conclusion. So we need as much knowledge about the spatial pattern of our density function as possible, because we could see on coarse grids it's all about computing the probability, and that transition from a probabilistic problem to the deterministic problem, it's based entirely on the properties of our density function. So anything that we know about it must be used to its fullest extent. Okay, so there are some reference to this work, and thank you for your attention.
Very much, Natalia. We have a bit of time for questions. So, are there questions? I wanted to ask you, just from a simple point of view of numerical analysis, the idea would be that you would have more efficient sampling if it was not a regular grid.
what I can tell for sure, it would be a much more sophisticated problem. With regular grids, we are able to do some theoretical work upon it. So because we have some idea how we can compute the probability density function. If we use a random grid, then things are getting much more sophisticated. I don't know actually what the results can be. There is some evidence in ecological literature that when they use a random grid, somehow they believe that they get more accurate evaluation. But once again, so this talk, so if I can go back to this diagram. Yep. Okay, so this is all about this diagram. And what is our chance to get close to this true value of the population abundance? And when we have a regular grid, at least we can predict so the chance. It can be high or low, but we can do something about it. If you have a random grid of points, then I'm not quite sure. So what happens there? So I don't know. So we have to investigate it in a similar way, but with one complicating factor that we have some extra randomness in our problem.
I agree. Yeah. David.
Thank you, Natalia, for the talk. Is there some connection with distance sampling statistics? You know what are distance sampling statistics? Distance sampling statistics is the statistics for the evaluation of population of living animals, where you want to make some transect and you want to evaluate the probability to lose an animal as the distance from the transect is increasing. And I think that there are some strong connection with your works and this kind of statistics, which is well known in big animals, statistics on big animals.
So from your description, seems to me that you have a temporal problem. So
it's only spatial problems. You want to know how many transects you have to do in the forest?
Yeah. In this case, yes. So if you just have a sort of snapshot,
yes.
Then yes, it's very similar then. Yeah.
Okay. Thank you.
Hello. Thank you for the talk. I'm just wondering whether you can incorporate measurement error into your framework and examine that as well.
Okay, that's a good question. And actually, we did that study, and again, so this talk basically is about this diagram, okay? And here we have a certain range, okay? And now if we incorporate the measurement arrows, and again, roughly speaking, you have to add noise to the maximum value and to the minimum one, okay? And depending on the noise, if your noise is not pretty strong, okay, so I'm talking about uncorrelated noise, you just perturb this range a little bit. And if you have something already, so if your single realization is far away from the true value and you perturb it a little bit, so you already have some rubbish, you perturb it a little bit, you have a different rubbish, but still rubbish, okay? Now, if you have something like this, yep, when the range is small and all values are close to the true value, and that may happen actually, and we could see it. Yeah. So for this distribution, that picture is true already when you have a coarse grid of points. And if you have this picture, when the range is small, okay, and you perturb it with noise, that yes, noise then change your results quite dramatically. So in theory, when you approach asymptotic convergence, then noise becomes a dominant factor, and you converge at the rate of square root of n. No matter how your method of evaluation will converge, okay? But that is just about asymptotic convergence. If you have a situation like this, then noise does not make things worse because they are already pretty bad. Okay, so you don't care actually.